All right, ladies and gentlemen, welcome to my Pencast. Today we're going to look at an electric field problem. Problem reads number 21. Two 2-centimeter diameter discs face each other 1 millimeter apart, and they are charged to plus and minus, meaning positive and negative, 10 nanocoulombs. First part of the question reads electric field strength between the discs is, and second part of the question reads there's a proton shot from the negative disc toward the positive disc. What launch speed must proton have to just barely reach the positive disc? So those are the two parts of the problem we're going to tackle today. First off, we're going to do a little visual representation of the discs we're working with. So since they are charged oppositely but equal in magnitude, we could see this as a parallel plate capacitor. So when we solve for the electric field, we're actually going to use the equation that applies to parallel plate capacitors. So here are all the dimensions, and here's a little proton. You can kind of see. So here we have, here is the negative disk, and here is the positive disk. All right. Now, let's start out with what we know and what we need to find out to get the electric field between the disks. So we know the separation between the two disks, which is 1 millimeter. So D equals 1 times 10 to the negative 3 meters, since 1 millimeter is equal to 1 times 10 to the negative 3 meters. Q, which is equal to charge, will be equal to 10 times 10 to the negative 9 coulombs, since nanocoulombs is equal to 10 to the negative 9 coulombs. Next, we will just simply write out the area equation for the disks, because we'll need to use that later for the electric field of a parallel plate capacitor equation. We also know the radius of the disks, because since we know the diameter, the radius is just 1/2 of the diameter. So it will read 1 times 10 to the negative 2 meters, since 1 centimeter is 10 to the negative 2 meters. Now let's see what we can do about this parallel plate capacitor equation. So here we go. So we can simplify A in this equation. Let's zoom in on this. We can simplify A in this equation to pi r squared. Now, substituting in for all the values, we get 10 times 10 to the negative 9 coulombs. And we know this constant here is 8.85 times 10 to the negative 12. And the area will be equal to pi r squared, and we have r, which is 1 times 10 to the negative 2 meters. So we solve for that, and the electric field in the middle of the plate capacitor is equal to 3.6. Messed up that 3 right there. Times 10 to the 6 newtons per coulomb. All right, now to start out with the next part of this problem. All right, so this was A. We solved for the electric field of the parallel plate capacitor. Now we're going to need to look at the launch speed of the proton such that it just barely reaches the positive disk. So since the proton is positively charged, the repulsive force coming from the positively charged disk will slow the launch speed of the proton such that the final velocity will actually be equal to 0. So let's just write down that VF is equal to 0. Now we're going to be looking at velocity now. What is the launch speed, the initial velocity? That's what we need to find out. So how can we relate electric field to velocity? Well, we know that force is equal to charge times electric field, or probe charge, sorry. This is the probe. And we know that acceleration is equal to force over mass. And then on top of that, we know that Vf squared minus Vi squared is equal to 2ax. And that's a kinematic equation from physics 1. All right, so using all three of these equations, we should be able to find out that a launch speed that should get the proton just barely to the positive disk. So we have E, the electric field already. We have the charge of the proton, which would be equal to, I believe, 1.6 times 10 to the negative 19 coulombs. We also can just plug that right in there, multiply that by the electric field that we just calculated for. Since the force will be acting on this proton, and that gets us 5.76 times 10 to the negative 13 newtons. Now let's use this acceleration formula. So we just calculated for force, so now we can just plug this in. 5.76 times 10 to the negative 13 newtons over, well, what's the mass of the proton? Well, all we have to do is look that up, and it is 1.76, or sorry, excuse me, 67 times 10 to the negative 27 kilograms. All right, and I apologize in advance for the camera quality. I'm doing this on my phone for the first time, don't really have a tripod. So we have mass, so that will be 1.67 times 10 to the 27 kilograms. And the acceleration will be equal to 3.45 times 10 to the 14 meters per second squared. I have that right here. Now, since the proton, which we drew over here, is going in this direction towards the positive sphere, the force that is acting on it, that's slowing it down and turning that final velocity into 0, is going the opposite direction. So we'll call this the force that's going on the proton. Since that's going in the opposite direction, we will define the positive direction of x as to the right and the negative direction to the left. So we'll actually change this to negative 3.45 times 10 to the 14 meters per second squared, because it's going in the opposite direction of the proton. Now all we have to do is use this kinematic equation to solve for the initial velocity. Now we already said that the final velocity is equal to 0. We know acceleration, we know x is just equal to the separation between the two disks, which is just d, so x equals d. So let's simplify this equation. Vi is equal to the square root of negative 2ax. So let's plug and chug. Negative 2, we have the acceleration now. It is negative 3.45 times 10 to the 14 meters per second squared. I'm going to move this out of the way. Let's put that up here. All right. Now x is just equal to d, and we said d up here was equal to 1 times 10 to the negative 3 meters, because it's 1 millimeter. All right. Now, solving for the initial velocity, we get in the end 8.3 times 10 to the 5 meters per second. So that was it. That was a long problem. I can kind of go over it again because I know that was probably hard to see everything. We drew out a little diagram showing the force on the proton. This is all we know from the start. Since they're both oppositely charged, we use the parallel plate capacitor equation for the electric field. We got 3.6 times 10 to the 6 newtons per coulomb. Then we need to find out the launch speed of a proton that was shot from the negative disk to the positive disk, such that it just barely touches the positive disk. And we know that the force of the positive disk is working against the proton, so we know that the final velocity will be equal to 0, so we'll be slowing it down. And since it's slowing it down, we know that the acceleration against the proton will be in the negative direction. So we solved for force on the proton using the electric field that we already calculated for, which is right here. We got 5.76 times 10 to the negative 3 newtons. Then we used that force and plugged it into the acceleration formula to find out what that acceleration was that was affecting the proton. Then we used the Vf squared minus Vi squared equals 2ax kinematic equation to find out that final velocity, or excuse me, the initial velocity, such that it finally reaches that positive disk. Finally, we got 8.3 times 10 to the 5 meters per second. So that was a long problem, but we made it through. Thanks for watching, guys.